Welcome to part 2 of TIA Portal version 16 STL tutorial. John, I'm going to see if we can get through this. So, previously we wrote debounce blocks in part 1, and they were written in ladder and in STL. And we used these to take an input, require it to be on for a set amount of time, and then we turn on an output. And if we turned off the input, we had to wait a set amount of time before the input would come off. So in this iteration, we have added a couple more rungs to take our input time, compare it to 100 milliseconds, and if it's less than 100 milliseconds, move 100 milliseconds into this temp verified set delay timer preset. And now we use this in our timer. We do the same thing with the off timer. And if we're greater than 100 milliseconds, then we move this value, our set delay time, directly into the timer. So let me see if I can give you a couple examples of how this works. I've got this dB tied into our inputs. So right now we have 100 milliseconds coming in, or 0 milliseconds coming in, and then we write out 100 milliseconds actually going into the timer we default to. So if I set this to time 2 seconds, now we can move through our alternate branch here. 2 seconds is greater than 100 milliseconds, therefore move 2 seconds into verified set delay timer preset. And if we come down here to that timer, now we have 2 seconds coming in. So we can turn on our input. It has to wait 2 seconds. It turns on, lets us through, and if we turn it off, it's almost instantaneous. It's 100 milliseconds on our off delay timer. So next we have, let's see what the equivalent would look like in STL. So our first network, I wrote out the mnemonics to help with this too in the comments. So we load our set delay time, and then we load 100 milliseconds, and then we do a compare right here. So this is loaded into accumulator 1, this is loaded into accumulator 2, and then we compare, and we write that result to the RLO. So we have 0 milliseconds coming in compared to 100 milliseconds, and then that makes our RLO positive 1. Then we do this load and transfer. But let's break this down. These 3 rows right here are the same as this instruction here. We're loading a value in, we're loading a value in, and then we're comparing. And then we take our RLO and we send it out. Then we load 100 milliseconds into accumulator 1, and then we transfer that to verified set delay timer preset. Load in our 100 milliseconds, and we transfer it to our verified set delay timer preset. It's essentially these 2 rows are a move instruction. If our RLO is positive, we're going to jump to network 2. So we come down here and we jump to network 2. What that keeps us from doing is executing any code here. If the RLO is negative in this situation, then it will allow us to run these instructions here. This is similar to the bottom part of the branch. We load our set delay time. We load 100 milliseconds. We make our compare. And then we load our set delay time and we transfer it to verified set delay time or preset. Again, these two instructions work as a move, and these three instructions work as a compare. And what the jump allows us to do is check if this condition's on, and we complete our move, and we skip making these operations here. So we get to network 2, and it's the same thing except for this is the off delay time, or the reset delay time. So we load our reset delay time, we load 100 milliseconds, we do our compare, then we can load and transfer. If our RLO is positive, then we can jump to network 3 and skip all of this code right here. Same thing as the other network. So what does this gain you? Well, there is sometimes instructions that you can do in STL that you can't do in ladder. In ladder, I had to add this temporary variable. It's a bool. I'm calling it null, in order to make this block compile. We couldn't leave the block like this. We had to have an output on it. So let's put that back and we're current. But we don't have to do that in STL. We can just write instructions and we don't have to worry about what the end of the run looks like. Out in the field, I've seen networks have hundreds of rows inside of networks. It does become a little difficult to manage, but it gives you a lot more creative capacity. Another thing to consider is I check the memory usage of this block versus that block, and our ladder debounce block used 9,600 bytes of load memory and 228 bytes of work memory. The STL debounce block used 7,903 bytes of load memory and 207 bytes of our work memory. When you have this debounce block 100 times in your program, that may be a big difference. At least on the older PLCs, that was part of why they did this. So that's where we're at with that. I'm a little curious to see how my friend Brock does, if he explains or shows us any different, but he's got some really good videos. I can post a link in my description so you can check out his videos and figure out where to go next with these. I'm thinking the next videos may work with, we'll dig a little bit deeper into jumps, maybe some breaks, and then maybe jump cases. Thank you for watching. Send me any comments if you'd like source code to this project so you can read along. Have a good day.